A Roman harbor wall built 2,000 years ago stands stronger than concrete poured 50 years back. This single fact holds a chemical secret modern science has only just uncovered. By the end of this, you will know exactly how to build a material that repairs its own cracks and grows stronger for centuries. We will reveal why seawater strengthens this ancient concrete instead of destroying it, and how a violent mixing technique forgotten by history creates a built-in repair kit. What does it say about our modern world when the best blueprint for the future was written in stone 2 ago? That harbor at I is not an isolated miracle. Across the Mediterranean, from Italy to Israel, similar structures defy the relentless sea. Wave after wave, century after century, the concrete not only holds, it seems to welcome the assault. This is the timeless Enigma. Modern marine concrete, engineered with our deepest scientific knowledge, is designed to resist seawater. Yet it often succumbs within decades, its steel reinforcements corroding, the material itself slowly crumbling. The Roman version, cast without any steel, performs the opposite. It appears to gain strength from the very element meant to destroy it. For centuries, scholars looked at the surviving ruins and the surviving texts. The Roman architect Vitruvius left detailed notes in his work, specifying proportions of lime and volcanic ash. But reading his words is like having a recipe without knowing the exact heat of the oven or the secret ingredient that makes the cake rise. The instructions were there, yet the full, miraculous chemical reaction remained within the stone itself. This left a gaping hole in our understanding. How could a 2,000-year-old formula outperform the pinnacle of modern material science? The answer was not just in what they used, but in how those ingredients talked to each other across the. To solve this, we had to look closer, much closer, at the microscopic world within a fist-sized chunk of Roman history. The secret begins not with a blueprint, but with the ground beneath their feet. On the fertile slopes of Mount Vesuvius, Roman builders a fine, sandy powder that looked utterly unremarkable. This was Pozzolana, named for the town of near Naples, and it was the magical first ingredient. To the naked eye, it was just gray dust, but under a microscope, it reveals itself as a shattered landscape of volcanic glass, rich in silica and alumina. This is the critical detail. When the volcano erupted, the molten material was blasted into the air and cooled so rapidly it couldn't form crystals, locking its reactive potential into a fragile, glassy state. The Romans, through brilliant empirical observation, discovered that this specific ash, when mixed with lime and water, didn't just sit there. It came alive. The lime, made by burning limestone, provided a highly alkaline environment. In that chemical bath, the glassy particles of Pozzolana begin to dissolve. Their silica and alumina react with the lime to form a stable, interlocking gel that binds the aggregate, the crushed rock and brick, into a single, incredibly resilient mass. This is the heart of the Roman binder. Modern Portland cement creates a brittle, crystalline structure when it sets, but the Roman Pozzolana lime paste forms a far more flexible, durable matrix, one that is inherently less prone to cracking. Think of it like this. Modern cement is like a sheet of ice, hard but prone to shattering. The Roman binder is more like a tough, dense gel, able to absorb stress and movement without failing. The Romans sourced this material with meticulous care, understanding that not all volcanic ash was equal. They sought out deposits from specific eruptions that gave the ash its perfect, reactive fineness. They then mixed it in precise ratios, recorded by Vitruvius, that we now know optimize the chemical reaction. This was ancient materials science at its finest, a technology born from observing the land itself. It makes you wonder, What other seemingly ordinary materials did past civilizations use, whose hidden properties we have yet to rediscover? With this reactive foundation in place, the real alchemy was ready to begin, but the perfect volcanic ash was only half the recipe. On a bustling Roman worksite, the real magic happened in the mixing pit. Modern builders typically use slaked lime, a cool, pre-reacted paste that is stable and easy to handle. The Romans did something far more dramatic. They started with quicklime, known as calcium oxide, a material created by roasting limestone in a searing hot kiln. This substance is highly reactive and dangerous on its own. When water is added, it doesn't just mix, it erupts. The slaking process is violently exothermic, releasing a tremendous burst of heat and steam. The Romans weren't just making paste, they were creating a boiling, reactive slurry. For a long time, historians assumed this hot mix was just an intermediate step, that the quicklime fully reacted with water to become calcium hydroxide before being combined with the ash and aggregate. But a groundbreaking study, led by researchers at the Massachusetts Institute of Technology and other institutions, turned that assumption on its head. They discovered the Romans were far more clever. They intentionally used large, millimeter-scale chunks of quicklime directly in the final concrete mix. These white, pebble-like inclusions, called lime clasts, were long dismissed as evidence of poor mixing or low-quality control, little more than ancient mistakes fossilized in the stone. The new research revealed they are nothing of the sort. They are the secret self-repair system, deliberately engineered into the material. Here is how the hot mixing process works on a chemical level. The intense heat from the slaking reaction does more than just create steam. It pushes the chemistry into a unique high-temperature pathway that encourages the formation of these specific calcium-rich lime clasts. As the concrete sets and hardens around them, these tiny white lumps become encapsulated, sitting dormant like microscopic repair kits scattered throughout the entire structure. Now picture a tiny crack forming in the concrete after centuries of stress. Seawater or rainwater finally seeps in, reaching one of these embedded lime clasts. The water reactivates it, much like the original slaking process on the worksite. The quicklime core rapidly absorbs water and carbon dioxide, expanding as it recrystallizes into a form of calcium carbonate. This new crystalline material fills the crack from the inside out, seamlessly welding it shut. It is a brilliant, passive repair mechanism designed by the Romans and powered by time itself. This means the very flaws we see in modern concrete, the cracks that spell the beginning of the end, are for Roman concrete an opportunity for healing. The material isn't just durable, it is literally alive in a chemical sense, capable of responding to injury. This discovery shifts our entire perspective. It shows the Roman builders weren't just following a recipe. They were masters of material thermodynamics, manipulating chemistry on a grand scale to bake resilience directly into their stone. But to understand the full picture, we must go even deeper, to the molecular dance that occurs when this self-healing concrete finally meets the sea. Deep within a sample from a Roman breakwater, under the gaze of a powerful electron microscope, scientists found a hidden forest, not of trees but of crystals. Two specific minerals and philipsite were growing in delicate, interlocking plates throughout the ancient concrete. This discovery was astonishing because these minerals are notoriously difficult to create in a lab, and in modern concrete, they are almost never seen or they quickly break down. Yet here they were, flourishing after 2,000 years. Their presence is not a coincidence. It is the signature of the concrete's long-term chemical conversation with the sea. In particular is a calcium silicate hydrate mineral that forms strong sheet-like structures. Think of it as nature's own microscopic reinforcement bar, a crystalline armor woven into the fabric of the concrete. It provides exceptional compressive strength, allowing the material to bear immense weight, while its plate-like shape also lends a degree of flexibility, preventing brittle fracture. Philipsite, a porous, needle-like mineral, often grows alongside it, adding to the complex, reinforcing network. The key insight is that these crystals did not exist when the concrete was first poured. They are not ingredients, they are offspring. They are born from the incredibly slow, patient reaction between the lime, the dissolved silica from the volcanic ash, and the minerals dissolved in seawater, particularly aluminum and potassium. Over decades and centuries, as seawater percolates through the concrete's pores, it continually feeds this slow-growing crystalline structure. The Roman recipe creates the perfect chemical nursery, a stable, alkaline environment where these minerals can nucleate and grow, strengthening the material from the inside out for generations. This process is so effective that materials scientists examining cores drilled from the ancient harbor of Caesarea have found dense, intricate networks of these crystals. Especially a form rich in aluminum called aluminum. The concrete there is literally more stone now than it was when the Romans left it. This raises a profound question for our modern world. We engineer materials for immediate strength, for the load they must bear tomorrow. The Romans, perhaps unintentionally, engineered for time. They created a system that uses time as an ingredient, allowing the environment to participate in the material's evolution, making it not just durable, but actively growing stronger. This understanding of the crystalline phases is the final piece that unlocks the full picture of self-healing. The lime clasts are the repair kits, and the growing crystals are the long-term structural upgrade. One handles sudden damage, the other ensures enduring resilience. This is not a theoretical concept. In a laboratory, scientists took a core sample of ancient Roman maritime concrete and deliberately fractured it. They then simulated the conditions of a Roman harbor, exposing the cracked sample to flowing seawater. Within 2 weeks, the results were undeniable. The crack began to fill in from the inside, sealing itself with a white, crystalline material. By the end of the experiment, the breach was completely healed. The concrete had literally repaired its own wound. This autonomous repair mechanism is the chemical secret modern science has rediscovered, and it hinges entirely on those embedded lime clasts we discussed earlier. Think of each tiny white inclusion as a microscopic reservoir of potential. When a crack forms and water finds its way in, it acts like a key, unlocking this reservoir. The water dissolves silica from the surrounding volcanic ash and calcium from the heart of the lime clast. These dissolved ions then travel through the crack, and where they meet, they precipitate out as a new, strong calcium silicate hydrate gel. This is the same essential binder that holds the original concrete together. So the repair isn't a patch or a glue, it is the creation of new concrete, grown in place to perfectly mend the flaw. For this process to work, several conditions align perfectly in Roman concrete. First, you need the reactive source of calcium, the quicklime clasts. Second, you need the reservoir of silica, the volcanic Pozzolana. Third, you need a trigger, which is simply the presence of water. It is a beautifully simple, passive system. Engineers now describe this as a paradigm shift in thinking. We have spent centuries designing static materials, substances we expect to remain exactly as we poured them, fighting a losing battle against the elements. The Roman approach was to design a dynamic, almost living material, one that is designed to change and adapt, using environmental exposure not as a threat, but as a source of renewal. A helpful analogy is the human body. When you get a minor cut, Your body doesn't just sit there. It mobilizes platelets and proteins to form a clot, then builds new tissue to close the wound from the inside out. Roman concrete operates on a similar principle of autonomous healing. This remarkable capability forces us to re-examine the role of a surprising element we once thought was purely destructive: seawater itself. Seawater was not the enemy of Roman concrete. It was the final, essential ingredient. Modern engineers view the ocean as a corrosive soup, a relentless force that attacks the steel inside our concrete, leading to rust, expansion, and eventual collapse. The Roman material flips this entire relationship on its head. For their concrete, the sea became a partner in a centuries-long chemical reaction, a source of ions that actively built new strength from within. This is the profound difference. Our concrete fights its environment, theirs collaborates with it. The secret lies in the ion exchange process. Seawater is rich in dissolved magnesium and sulfate ions. When this brine percolates through the porous Roman concrete, it encounters the highly alkaline environment created by the lime and the reactive surfaces of the volcanic ash. Here, a slow, transformative trade begins. The magnesium ions in the seawater swap places with some of the calcium and aluminum ions in the concrete's binder. This exchange doesn't weaken the structure, it reinforces it. The magnesium and aluminum combine to form delicate, layered minerals called. These minerals act like microscopic sponges, locking up chloride and other potentially harmful ions that would otherwise cause damage. They become a built-in filtration system, purifying the concrete's internal chemistry as they grow. Simultaneously, the sulfate ions contribute to the formation of more strengthening crystals which fill pores and add to the material's density. Marine chemists studying this process note that the Romans, through brilliant trial and error, created a material perfectly tuned to its marine environment. The concrete wasn't just dumped into the sea, it was designed to mature there. Constant immersion provided a steady, slow feed of these reactive ions, allowing the beneficial chemistry to proceed at a geological pace. This long-term maturation is why cores from ancient harbors show the concrete gets harder and more crystalline the closer you get to the surface exposed to the waves. Contrast this with the fate of a modern marine pier. The chloride ions in seawater penetrate the concrete and reach the steel rebar. They break down the protective layer on the steel, initiating rust. Rust occupies more volume than the original steel, creating immense internal pressure. This pressure cracks the concrete from the inside, causing chunks to spall off in a process known as concrete cancer. The structure literally blows itself apart. It is a battle of attrition that the concrete, designed as a static shield, is destined to lose. Now picture a site where both materials exist side by side, a modern repair sitting atop 2,000-year-old Roman foundations. The modern section shows cracking and decay within decades, while the ancient block below remains monolithic, its surface smoothed by the sea but its integrity utterly intact. This visible contrast forces a fundamental question about our own approach. For over a century, we have pursued materials of immense but brittle strength, designed to dominate their surroundings. What if, instead, we design materials to listen to their environment, to adapt and draw strength from it? The Roman concrete suggests that resilience isn't about resistance alone, it is about forming a chemical partnership. This partnership points to a deeper divide in how knowledge itself was built, separating the Roman hands-on, empirical mastery from our modern, theory-driven science. The Roman engineers were masterful practical chemists, yet they never saw a single molecule. For generations, through relentless trial and error on harbors and aqueducts, they perfected a recipe that worked miracles. They knew the exact proportions of ash to lime the importance of a violent hot mix, and the necessity of immersing it in seawater. This was prescriptive knowledge, a set of brilliant instructions passed down through guilds and texts like that of Vitruvius. He meticulously recorded the what and the how, but the underlying mechanistic why, the atomic dance we can now observe with electron microscopes, remained a complete mystery to them. They crafted a symphony without ever learning music theory. This gap between flawless practice and unknown principle is what made the knowledge so fragile. When the Roman world changed, the intricate chain of apprenticeship and practical tradition was broken. The recipe, devoid of its scientific explanation, became a cryptic artifact, a set of steps whose profound purpose faded from memory. Historians of technology note this is a common pattern. A society can achieve incredible technological heights through accumulated empirical wisdom, but without the descriptive knowledge of underlying principles, that wisdom can vanish as quickly as it appeared. The concrete formula did not disappear overnight, but its understanding did. Later builders might have used similar-looking ash, but without the specific volcanic source or the precise hot mixing technique, the magic was lost. The knowledge became a ghost in the historical record, a reminder of what was once possible. This sets the stage for a pivotal moment centuries later, when a new world with new priorities would look back at the ancient ruins and make a conscious, but ultimately flawed, choice. The Industrial Revolution demanded speed above all else. Cities were exploding upward, factories needed foundations now, and railways required bridges at a pace never before imagined. This new era prized rapid setting, consistent, and easily manufactured materials. The slow, patient chemistry of Roman concrete, which gained strength over decades, was incompatible with the rhythm of the 19th century. Portland cement, patented in 1824, was the perfect answer. It could be produced anywhere from standardized materials, it set predictably and quickly, and it offered immense short-term strength. But in the race for rapid progress, the ancient benchmark of durability was quietly left behind. The choice was economic and social, not scientific. We traded longevity for immediacy, a long service life for a 50-year timeline. There is a telling anecdote from the 18th century, when British engineers tried to replicate Roman concrete to build lighthouses capable of withstanding the fierce North Sea. They studied Vitruvius, they sourced volcanic materials, but lacking the key insight into hot mixing and the self-healing lime clasts, their attempts failed to capture the legendary durability. They had the prescription, but not the deeper description, so the material behaved like a feeble imitation. This historical disconnect makes the modern rediscovery so significant. For the first time, we are closing the loop. We now possess both the prescriptive knowledge from the ancients and the descriptive, scientific understanding of why it works. We can see the lime clasts not as mistakes, but as engineered features. We can watch the crystals grow. This fusion of ancient empirical wisdom and modern analytical science opens a door not just to replicating the past, but to evolving beyond it. It prompts a question for our own era. What brilliant empirical solutions have we already invented, waiting for future science to reveal why they truly work for decades? The lime clasts were dismissed as a simple mistake, an imperfection in an otherwise perfect material. It was a classic cold case, a 2,000-year-old mystery written in stone and waiting for the right detectives with the right tools. The breakthrough did not come from a single brilliant mind, but from a global collaboration, a meeting of disciplines that had previously worked in separate worlds. Geologists who understood how rocks form sat down with materials scientists who could probe the atomic structure of modern cement, and archaeologists who could provide pristine samples from long-buried Roman sites. This fusion of perspectives was the key that finally turned the lock. The investigation played out in laboratories across the world, from the Massachusetts Institute of Technology to the University of Utah. The tools were as advanced as the mystery was ancient. Researchers employed techniques like synchrotron X-ray diffraction, which uses incredibly bright, focused X-ray beams to map the crystal structure of materials at the nanoscale. They used Raman spectroscopy, a method that shines a laser on a sample and analyzes the scattered light to identify the chemical bonds present. Think of these tools as molecular fingerprint scanners, allowing the scientists to see not just what the concrete was made of, but how those atoms were arranged and bonded together. They were no longer just looking at a rock, they were reading its chemical autobiography. One pivotal sample came not from a famous harbor, but from the city walls of an ancient Roman town. This terrestrial concrete, sheltered from seawater, still contained those telltale lime clasts. By comparing it to marine samples, the team could isolate the effects of the hot mixing process from the later influence of the sea. Under the microscope, the evidence became undeniable. The chemical composition and the crystalline structure of the lime clasts were consistent with a rapid, high-temperature formation, exactly what the violent hot mix would produce. They were not lumps, they were deliberately created, highly reactive reservoirs. The lead researcher from the Massachusetts Institute of Technology described the moment of realization as a profound shift. We stopped seeing them as defects and started seeing them as functional components. It was the eureka moment that rewrote the recipe. The timeline of hypotheses itself tells a story of scientific evolution. Earlier theories had focused on the rarity of the volcanic ash or some lost, mystical ingredient, but the new data pointed conclusively to the process, not just the components. The detective work mapped a clear path from the roaring heat of the Roman mixing pit to the encapsulation of the quicklime chunks, to their eventual role in crack healing centuries later. Every microscopic clue lined up. The aluminum-rich crystals growing in the marine samples confirmed the long-term strengthening reaction with seawater, while the pristine lime clasts in the land-based concrete confirmed the recipe's intentional design. The case was closed. The Romans had engineered a self-healing material, and modern science had finally decoded its blueprint. This hard-won understanding, pulled atom by atom from ancient stone, now presents us with the most exciting question of all. We have the forensic report, we have the original recipe and the scientific explanation. So what do we build with it? The blueprint for a new era of construction is no longer hypothetical. The most immediate and transformative application of this rediscovered knowledge lies where the land meets the sea. Civil engineers are now actively exploring a new class of material, often termed Roman-inspired concrete, or RIC, specifically designed for the brutal, saline environment of our coastlines. The vision is clear. Imagine breakwaters that do not slowly erode, but instead grow more resilient with each passing storm. Picture offshore wind turbine foundations that require minimal maintenance over their entire operational life. They're concrete chemically partnered with the ocean rather than corroded by it. The goal is to move beyond mere resistance, to create marine infrastructure with a service life measured in centuries, not decades. This isn't science fiction, it's a direct translation of ancient chemistry into modern engineering priorities. The formulation begins by replacing the traditional Portland cement with a blend of lime and modern. While the volcanic ash is still prized, Researchers have identified powerful alternatives in industrial byproducts like fly ash from coal plants and slag from steel production. These materials are rich in the same reactive silica and alumina that made the Roman ash so potent, turning waste into a critical resource for durable construction. The mix would then incorporate the deliberate, engineered inclusion of lime clasts, creating that built-in self-repair network from the very beginning. The process would be optimized with modern quality control, but the core chemical principles remain those discovered too ago. The benefits are twofold: economic and environmental. From a cost perspective, the reduction in maintenance is staggering. A tidal barrier built with self-healing concrete would not need the constant, expensive patching and replacement that plagues current structures. The initial investment might be higher, but the total cost over 100 or 200 years would be far lower, freeing public funds for other vital needs. Environmentally, the production of lime-based RIC generates significantly less carbon dioxide than traditional Portland cement, which is a major global contributor to greenhouse gas emissions. Furthermore, by utilizing industrial byproducts, the formula helps close a waste loop. Consider a practical case study: a coastal city like Miami or Rotterdam, facing rising sea levels and increasingly powerful storms. Their current defenses are a patchwork of concrete and steel, requiring vigilant and costly upkeep. A new generation of sea walls, built with Roman-inspired concrete, would be designed to last. As seawater permeates the structure, it would not trigger a decay spiral, but would instead encourage the growth of strengthening minerals within the pores. Minor cracks from seismic shifts or impacts would seal autonomously. The wall would become a permanent, evolving part of the coastal landscape, a legacy project in the truest sense. This raises a reflective question for our society: what kind of legacy do we wish to build? We have grown accustomed to infrastructure with an expiration date, planning for obsolescence. What if we shifted our mindset to plan for permanence, to create public works that our great will still rely upon, not as crumbling relics, but as fully functional testaments to foresight? The potential of this material, however, extends far beyond the shoreline. But the most profound test for any material lies far from the shore, buried deep within the earth. Contemplate the ultimate challenge of durability, safely isolating radioactive materials from the biosphere for tens of thousands of years. This is the timescale of geological epochs, far beyond the of any civilization. For this monumental task, nuclear materials scientists are looking with intense interest at the principles behind Roman concrete. The proposal is to use a Roman-inspired formulation for the structural barriers and encapsulation layers in deep geological repositories, places like Finland's facility, carved into stable bedrock. The reasoning is compelling. These repositories are designed to be passive safety systems, requiring no future maintenance. The engineered barriers around the waste must remain stable and impermeable even as the ground subtly shifts and water slowly percolates through the rock. This is where the ancient material's properties become not just useful, but potentially revolutionary. Modern Portland cement-based concretes can degrade over long periods in the predicted chemical conditions underground, a process that could compromise containment. A Roman-inspired blend, however, is designed for exactly this kind of long-term chemical evolution. Its key strength is mineralogical stability. Over centuries, as we have seen, it transforms, forming crystals-like, and that actually lower its permeability, making it less likely to transport dissolved material. More importantly, its self-sealing capability addresses a critical vulnerability. If a tiny were to form in a tunnel lining or encapsulation shell due to seismic activity or pressure, groundwater could ingress. In a Roman-inspired matrix, that water would activate the embedded lime clasts, precipitating new calcium silicate hydrate gel to autonomously seal the breach from the inside. This is a fail-safe mechanism engineered into the very fabric of the barrier. Researchers are actively studying specific properties for this application. They are testing the material's resistance to radiation-induced damage, ensuring the crystalline structure remains intact. They are measuring its long-term permeability under constant saturation, confirming it grows denser over time. They are modeling its chemical interactions with the other barrier components, like bentonite clay and the copper or steel waste canisters themselves, to ensure a harmonious, stable system for the ages. The repository, designed to hold spent nuclear fuel securely for 100,000 years, embodies this barrier philosophy. Incorporating a concrete that actively strengthens and self-heals would be a monumental upgrade to its defensive depth. This extreme application illuminates the material's profound potential in a new light. It shows that the Roman formula offers something even more valuable than longevity. It offers predictable evolution. We can model, with a high degree of confidence, how its mineralogy will change over 1,000 years, because we have 2,000-year-old samples that show us the finished product. This provides a rare certainty in the face of an almost unimaginable timescale. Furthermore, by utilizing industrial byproducts like fly ash this approach simultaneously addresses another modern crisis: carbon emissions. It replaces high-emission Portland cement and sequesters waste material into a permanent, stable stone. So from protecting our coasts to guarding our deepest legacies, this ancient technology offers a radical blueprint, one that asks us to build not just for our time, but for time itself. The billowing smokestacks of a modern cement plant represent a hidden cost of our built world. This single industry is responsible for roughly 8% of all global carbon dioxide emissions, a staggering figure that places it among the largest contributors to climate change. The process is inherently carbon-intensive. To create Portland cement, limestone, which is calcium carbonate, is fed into massive rotary kilns heated to around 1,450 degrees Celsius. At this blistering temperature, the limestone undergoes calcination, breaking down into lime or calcium oxide, and releasing carbon dioxide directly into the atmosphere. This is a chemical inevitability, not just a byproduct of burning fuel. For every ton of cement produced, nearly a ton of carbon dioxide is released. It is the environmental price of our speed and scale. Now shift your perspective to the Roman method. Their primary binder started with lime as well, but the process diverges critically. Lime production still releases carbon dioxide during calcination, but the overall carbon footprint of the Roman-inspired system is dramatically lower for several interconnected reasons. First, the temperature required to produce high-quality lime is several hundred degrees lower than that needed for Portland's cement clinker. This means less fuel is burned, resulting in lower emissions from energy use. Second, and more importantly, the Roman formula uses far less lime overall. In a modern concrete mix, Portland cement is the sole binder. In a Roman-inspired mix, the lime is not the star, it is the catalyst. Its role is to activate the volcanic ash or its modern equivalent, which provides the bulk of the long-term binding strength. This drastically reduces the quantity of processed lime required per cubic meter of concrete. The real game changer, however, is the itself. The Romans used natural volcanic ash. Today, we have a vast, untapped resource in industrial byproducts. Fly ash from coal-fired power plants and ground granulated blast furnace slag from steel production are not just waste materials. They are highly reactive sources of silica and alumina, the very ingredients that made Roman concrete so durable. Using these materials in a Roman-inspired binder achieves two monumental environmental goals at once. It diverts millions of tons of industrial waste from landfills, and it displaces the need for huge quantities of carbon-intensive Portland cement. Sustainability researchers have modeled the potential impact. A widespread shift towards these alkali-activated materials, often called, could reduce the carbon emissions associated with concrete production by as much as 80%. This isn't a marginal improvement, it is a transformation of one of the world's most foundational industries. Consider a simple comparison. The construction of a mid-rise apartment building using conventional concrete might embody the carbon equivalent of hundreds of tons of carbon dioxide, locked into its structure from day one. A similar building using a Roman-inspired concrete, with a binder based on lime and industrial slag, could cut that embodied carbon by half or more. Over the building's vastly extended, with minimal need for repair or replacement, its lifetime carbon footprint becomes almost negligible compared to a structure that might need to be rebuilt twice in the same period. This analysis is crucial. We must account not only for the emissions from making the material, but the emissions saved by its endurance. That lasts 500 years without major repair, eliminates the recurring carbon cost of demolition, disposal, and reconstruction of a wall that fails every 50. The economic benefit aligns perfectly with the environmental one. The raw materials for this green concrete, like fly ash and slag, are often low cost or even have negative cost, as industries pay to dispose of them. While the mixing process requires careful formulation, the overall material costs can be competitive, and the long-term savings on maintenance and replacement are enormous. This synergy poses a compelling question for our time. We face a climate crisis driven by industrial emissions, and simultaneously, we generate mountains of industrial waste. What if the blueprint for binding one problem to the solution of the other was written not in a modern laboratory, but in the pages of Vitruvius? The Roman concrete formula offers a path to turn the liabilities of our industrial age into the literal foundations of a sustainable future. This convergence of ancient wisdom and modern necessity reveals that the most advanced material for tomorrow might be one that remembers its past. The true cost of a bridge is not measured at its ribbon cutting, but across the centuries that follow. Our modern economic model for infrastructure is built on a simple, powerful illusion: the primacy of the upfront bid. When a city needs a new or a state plans a major highway interchange, the procurement process is typically designed to select the lowest initial construction cost. This makes immediate budgetary sense, but it tragically ignores the financial reality of the next 50 or 100 years. The concrete we choose today becomes a financial commitment for generations to come, a commitment to either endless repair or graceful endurance. To understand the economic genius hidden in Roman concrete, we must shift our accounting from decades to centuries, embracing a concept called cost analysis. This is the total cost of ownership for a piece of infrastructure, adding together the initial construction cost and every single expense that will follow: maintenance, repairs, eventual replacement, and even the social costs of traffic disruption and detours. When viewed through this lens, the financial picture transforms completely. A modern marine structure, built with conventional steel-reinforced concrete, might have a tempting low initial price tag. but its design life is often only 50 years, after which it requires major rehabilitation or complete demolition and rebuilding. Over a single century, that structure might need to be paid for twice, with decades of expensive patchwork repairs in between. Each repair cycle closes lanes, diverts shipping, and costs taxpayers millions. These are not unexpected emergencies, they are the predictable, baked-in cost of a short material. Now model the alternative. A Roman-inspired concrete, engineered with self-healing lime clasts and binders, comes with a higher initial cost. The specialized mix design and quality control add expense at the outset. But its service life is projected not in decades, but in multiple centuries, with minimal maintenance required. Over that same 100-year period, the financial comparison is stark. The conventional wall accrues a mountain of costs: initial build plus major repairs at year 30 and 60, plus a full rebuild at year 100. The Roman-inspired wall has one cost: the initial build, and perhaps some minor, superficial upkeep. Public policy experts who study infrastructure investment point to a systemic failure in our building codes and funding models. They are optimized for short political cycles and constrained annual budgets, not for intergenerational legacy. The procurement officer who approves the more expensive, durable option today might not see the savings realized within their career, while the budget director who chooses the cheaper option creates a long-term liability for future administrations. This is a profound misalignment of incentives. Economists use a tool called net present value to compare these long-term costs fairly, discounting future expenses to today's dollars. Even using conservative estimates, the net present value of the century-long cost for the durable concrete is almost always lower. The savings from avoiding just one major rebuild 30 years out often outweighs the higher initial investment. Consider a real-world scenario: the foundation piles for a coastal bridge. Conventional piles, suffering from chloride-induced corrosion, might need extensive cathodic protection systems installed after 25 years, a $1 million project that requires barges, divers, and lane closures. A pile made with a Roman-inspired mix would inherently resist chloride penetration and self-heal. The initial pile is more expensive, but the 25-year repair budget drops to nearly zero. The economic argument extends beyond balance sheets to societal resilience. Every day a major bridge or tunnel is under repair is a day of lost productivity, delayed shipments, and community frustration. A durable infrastructure asset provides uninterrupted service, a steady, reliable backbone for the economy it supports. This long-view economics forces a philosophical question upon us: what do we truly value? Do we value a low number on this year's budget report? Or do we value creating public works that will inherit not as burdens, but as gifts? The Roman concrete does not just offer a better material, it challenges us to adopt a better measure of value, one that honors the future as much as the present. 2,000 years of progress, and we are only now catching up to a forgotten standard of durability. This journey from Roman harbors to modern laboratories forces a humbling question upon our age of innovation. With supercomputers modeling stress and satellites mapping resources, why did the superior solution remain hidden in plain sight, encoded in ruins we have walked past for centuries? The answer is not a lack of intelligence, but a difference in perspective, one that reveals a critical blind spot in our modern approach to problem solving. We became masters of analysis, but perhaps we forgot how to observe on a grander scale. The Romans did not have material science, but they had something equally powerful: a deep, patient empiricism rooted in the long-term consequences of their choices. They built, they observed what lasted, and they refined their methods over generations. This is a form of learning from history itself, a practice we might call, where the past becomes a living laboratory showing the results of experiments conducted across. Philosophers of science point to a recurring pattern in technological advancement, a hubris that emerges when a new paradigm proves overwhelmingly successful. The invention of Portland cement gave us unprecedented control and speed. It worked so well for the urgent needs of industrialization that we stopped asking if it was the best solution, only if it was the fastest and cheapest. Our specialization into ever narrower fields of expertise, while driving incredible progress, can also create intellectual silos. A materials chemist may not regularly converse with a marine archaeologist, and a civil engineer might not study ancient Latin texts. This fragmentation meant the clues to a better concrete were scattered across disciplines, unseen until a collaborative effort brought them together. The rediscovery is a powerful argument for deliberate interdisciplinary thinking, for creating spaces where geologists, historians, and engineers can share puzzles and insights. It proves that the next great leap in a field may not come from deeper specialization within it, but from a connection to something seemingly unrelated. There is a profound lesson in how the Romans tailored their material to its environment. They did not seek a one-size-fits-all concrete. For a harbor, they used a specific volcanic ash and embraced seawater. For a land-based aqueduct, they might adjust the formula. This is a precursor to what we now call performance-based design, where the material is engineered for a specific function in a specific context. They were not just making concrete, they were growing a stone that belonged where it was placed. A helpful analogy lies in modern software development, particularly the Agile method. The Roman approach was strikingly iterative. They had a core recipe, the equivalent of a minimum viable product. They deployed it in the real world, the ultimate testing environment. They observed its performance over years and decades, the long-term user feedback. Then, they iterated, subtly adjusting mixes and methods for the next project. Their version of Agile development operated on a generational timescale, with each new harbor or bridge building upon the lessons of the last. This invites a reflective pause. What other forms of ancient wisdom have we discarded in our rush toward the new? Consider the passive cooling techniques of desert architecture, the earthquake-resistant flexibility of traditional timber joints in Japan, or the hydrological genius of Inca terrace farming. These are not primitive tricks, they are sophisticated adaptations honed by time. They represent a deep dialogue between human need and environmental reality, a dialogue we often short-circuit with brute force applications of energy and material. The story of Roman concrete is a case study in recovering that dialogue. It teaches a methodology of humility where we look to the long-term results nature has already provided. We must learn to see ancient ruins not just as monuments, but as data sets, as completed long-term experiments showing what truly endures. This shift in perspective prepares us to finally move from philosophical lessons to practical application. To build for the ages, we need more than admiration, we need the actual recipe. The next step is to translate 2,000-year-old principles into a modern instruction manual, to understand not just why it worked, but how we can mix it ourselves today. The recipe is not locked in a vault, it is written in stone and scattered across ancient texts. In a modern laboratory, researchers have become culinary historians of a lost art, attempting to recreate the exact chemical signature of Roman concrete. Their workbench holds not beakers of mysterious solutions, but precise digital scales, bags of volcanic ash, and chunks of limestone. The goal is not just to understand the theory, but to physically rebuild the process as the Romans did, measuring by volume as they would have, mixing by hand to feel the material's transformation. This is experimental archaeology in its form, a dialogue between ancient instructions and modern verification. The foundational text is Vitruvius's. In its pages, he prescribes a ratio, not by weight but by volume, a practical measure for builders on a dusty worksite. 1 part slaked lime to 2 parts pozzolana, the volcanic ash, to 9 parts of aggregate, the crushed rock or brick. This 1:2:9 ratio provides the structural blueprint. The lime is the activator, the pozzolana is the reactive heart, and the aggregate gives it bulk and strength. But reading Vitruvius is only the first step. The real challenge begins with sourcing. Not all volcanic ash is created equal. The specific glassy, fine-grained pozzolana from the region has a unique chemical fingerprint that modern substitutes must match. Researchers often seek out similar deposits or use characterized industrial byproducts to mimic its reactive silica content. Then comes the lime. The Romans did not use the stable, pre-slaked paste we buy today. They began with limestone, heating it in a kiln to around 900 degrees Celsius. This calcination process drives off carbon dioxide, leaving behind quicklime, a caustic, pebble-like substance that reacts violently with water. In the lab, this step is carefully controlled, replicating the ancient kiln conditions to produce material with the same high reactivity. The mixing stage is where theory meets dramatic, tangible reality. Following the volumetric recipe, researchers combine the dry quicklime with the pozzolana and the coarse aggregate, often a lightweight volcanic stone like tuff. Then, water is added. This is not a gentle stirring. The mixture erupts. The quicklime undergoes a slaking reaction with the water, releasing a surge of heat and steam, the temperature spiking dramatically. This hot mixing is not a side effect. It is the engineered core of the process. The intense, localized heat helps form those critical lime clasts and pushes the chemistry toward the desired mineral pathways. The consistency is crucial, described by those who have done it as a thick, almost mortar-like paste that is workable but holds its shape. For underwater placements like the harbor piers, the Romans used a brilliant adaptation. They would build wooden forms directly in the sea, then pour this hot mix into them. The seawater would not dilute the paste, but would immediately begin its long-term chemical partnership with it, helping it to set into a solid monolith beneath the waves. One experimental team documented their attempt to cast a small block using this full ancient method. They reported the palpable heat radiating from the mix, the challenging workability of the material, and the long, slow curing time, a stark contrast to the rapid set of modern concrete. After weeks, they tested their block, finding it already possessed remarkable compressive strength, a promising sign of the chemistry at work. This hands-on replication does more than verify a recipe. It builds an intimate appreciation for the Roman builder's skill. They managed this dangerous, exothermic reaction on an industrial scale, without thermometers or safety gear, relying on experience and tradition to produce a material that would outlast their civilization. To hold a piece of laboratory-made Roman concrete is to hold a bridge across two, a physical key to a past that is still teaching us how to build for the future. The Pantheon in Rome has stood under an open sky for nearly 1900 years, its vast dome of concrete still the largest of its kind in the world. This is not just a beautiful ruin, it is a continuous 2,000-year-long experiment in material science, and the data is unequivocal. Every surviving Roman structure, from the soaring arches of the aqueducts to the submerged harbor walls, serves as a living laboratory, offering direct observational proof of the concrete's legendary durability. Structural engineers and conservators now treat these monuments not merely as historical artifacts, but as case studies in long-term performance. They use invasive techniques like ground-penetrating radar to map internal stress and thermal imaging to detect moisture variations, all to understand the health of these ancient giants. The Pantheon's dome, a perfect hemisphere of poured concrete, has withstood countless earthquakes. Core samples taken from its thick walls reveal the same dense, crystalline microstructure of aluminum, and the same embedded lime clasts we find in marine concrete, proving the recipe's consistency. Seismic modeling shows the dome's ingenious design, with its graduated aggregate getting lighter toward the top, distributes gravitational and lateral forces with an elegance that still informs modern engineering. Each iconic site tells a different chapter of this endurance story. The Colosseum's massive skeleton has endured not just the weight of crowds and the passage of time, but relentless freeze-thaw cycles. Water seeps into micro cracks, freezes and expands, a process that rapidly destroys modern concrete. Yet the Roman mortar, with its flexible, binder and self-healing potential, has resisted this cyclical assault. The aqueducts, like the Gard in France, stand as linear monuments to chemical resilience, their channels having carried water for centuries while exposed to weathering, root intrusion, and mineral deposition. But perhaps the most convincing evidence comes from the marine works. At the harbor of Caesarea, archaeologists have drilled core samples from breakwaters that have been pounded by Mediterranean storms since the time of Herod. The concrete retrieved is not a crumbling relic. It is harder and more consolidated at the waterline than it is in the sheltered center. The constant flux of seawater has done exactly what the chemistry predicts. It has fostered the growth of strengthening minerals, turning the concrete into a rock that is literally more formidable now than when it was cast. A quieter, but equally telling, example is the tomb of On the Way. This massive cylindrical drum, built of concrete faced with travertine, shows almost no signs of structural degradation after Its exposure to wind, rain, and temperature shifts has resulted in only superficial wear, a testament to the material's resistance to atmospheric weathering. This collective archaeological record forms an irrefutable body of evidence. We are not relying on theoretical models or accelerated lab tests. We are examining the finished product after it's full of environmental stress. The structures themselves are the data, and they report a single, powerful finding. This concrete does not just endure, it thrives under conditions that defeat modern counterparts. This empirical validation from 2,000 years of real-world testing raises the final, and most urgent, question, now that we hold this proven blueprint for the ages. What will we choose to build the Pantheon's silent testimony now echoes in modern laboratories, where researchers are translating ancient principles into tomorrow's building codes? This is not the end of the story, but the beginning of a new chapter, one filled with open questions and active experiments. The core challenge is no longer understanding why Roman concrete works, but mastering how to reliably produce it at the scale of our global civilization. Scientists in international consortiums are tackling a series of intricate puzzles, each one a key to unlocking the material's full potential for the 21st century. One of the most pressing frontiers is scaling up the hot mixing process. In a Roman worksite, laborers mixed batches by hand, feeling the heat and adjusting intuitively. In a modern industrial plant, Giant rotating drums mix thousands of cubic yards of material. How do you replicate the precise, violent reaction that creates the perfect lime clasts within a massive, automated mixer? Researchers are experimenting with injection systems and mixing sequences, trying to ensure those microscopic self-repair kits are evenly distributed throughout every truckload. A feat of chemical engineering the Romans achieved through sheer craft. Another frontier is the search for a universal recipe. The Romans had the luxury of using specific local materials, the volcanic ash from, the lime from. For global adoption, we need formulas that work with aggregates and available anywhere. This has led to extensive studies on industrial byproducts. Can fly ash from a power plant in India perform as well as slag from a steel mill in Germany when activated by lime? The answer appears promising, but requires meticulous calibration for each regional material source to guarantee consistent, century-spanning performance. Long-term behavior in diverse environments is another major study. We have 2,000 years of data on maritime concrete, but what about Roman-inspired mixes in arid deserts, polluted urban centers, or regions with extreme freeze-thaw cycles? Accelerated aging tests in environmental chambers are simulating decades of exposure in months, but the true test will be the pilot structures now being planned. These field trials are the critical bridge between laboratory success and real-world trust. A compelling example is taking shape in coastal restoration projects. Imagine an artificial reef or breakwater block, not made of inert concrete, but of a Roman-inspired mix designed to heal cracks from wave impact and actively foster marine life colonization. The porous, mineral-rich surface could become an ideal substrate for oysters and corals, turning infrastructure into a living ecosystem. This synergy between structural function and ecological benefit is a powerful new direction. Beyond traditional construction, the material's properties are inspiring radical applications. Its ability to set without rapid water loss makes it a candidate for large-scale three-dimensional printing of structures, layer by layer. Its chemical affinity for carbon dioxide is being explored for carbon sequestration, turning a concrete wall into a passive sink that slowly pulls greenhouse gases from the air and mineralizes them within its matrix. These possibilities stretch the imagination, asking what other latent properties of this ancient formula await discovery. Could its thermal mass be tuned for passive climate control in buildings? Might its mineral evolution be harnessed to filter pollutants from water? The research agenda is vast. Yet, for all the scientific promise, significant barriers to adoption remain. Building codes are conservative by necessity, written around decades of data on Portland cement. Introducing a new material class requires years of rigorous certification. The construction industry is built on familiar, low-risk processes and supply chains. Convincing engineers, contractors, and project owners to choose a higher initial cost for a long-term benefit demands a fundamental shift in how we value time and legacy. The work in labs today is as much about generating that irrefutable performance data as it is about perfecting the mix. It is about creating a new standard, one where durability is not an optional luxury, but the foundational expectation. This journey from rediscovery to revolution hinges on our willingness to learn not just from the Romans' recipe, but from their patience to build for a future we will never see. Trusting that the chemistry we start will be perfected by time itself, the greatest obstacle to a new material is often not its science, but its timing. We have a proven blueprint for concrete that lasts centuries, yet our world is still built on a 50-year standard. This gap between what is possible and what is practical defines the current reality for Roman-inspired concrete. The core challenge is not a flaw in the formula, but the immense inertia of a global system designed around Portland cement. Building codes, the legal rulebooks for construction, are written in its language. For over a century, every safety test, every structural calculation, and every approved specification has been based on the behavior of this one material. To introduce a new class of binder is to propose rewriting a foundational chapter of engineering law, a process that is inherently slow, expensive, and risk-averse. Industry consultants who specialize in material certification describe a year journey. A new mix must undergo thousands of hours of accelerated aging tests, seismic performance modeling, and fire resistance trials to generate the data required for even a provisional code approval. This upfront research and development investment is substantial, and it falls on material producers who must gamble millions without any guarantee of market acceptance. The supply chain presents another formidable wall. From the quarry to the ready-mix truck, every link is optimized for Portland cement. Cement plants are massive capital investments designed for one specific chemical process. Retrofitting them, or building new facilities for a lime-based process, requires a financial leap that few companies are willing to make without a clear, immediate demand signal from large-scale projects. On the construction site itself, practical habits collide with ancient chemistry. Modern fast-track schedules are built on the predictable, rapid curing of Portland cement. A floor can be poured and be ready for heavy machinery in days. Roman-inspired concrete, with its slower, more patient curing and strength gain, could disrupt these tightly sequenced timelines, at least until new scheduling practices are developed. Contractors and crews are trained to work with the familiar material, understanding its feel, its set time, and its quirks. Introducing a different mix with a hot mixing process and different handling requirements demands retraining and introduces a perceived risk of error. The economic equation, while favorable in the long term, is challenging at the point of purchase. The initial cost per cubic yard for a high-performance Roman-inspired mix is currently higher, due to specialized ingredients and smaller-scale production. While cost analysis proves its superior value, public and private projects are often awarded based on the lowest initial bid. A procurement model that inherently penalizes materials with higher upfront costs but lower lifetime expense. An apt analogy is the early adoption of renewable energy. Solar and wind power were technically superior in many ways to fossil fuels, offering clean, sustainable energy. Yet for decades, they struggled against an entrenched ecosystem of power plants, pipelines, and political interests built around coal and oil. Their breakthrough required not just better technology, but policy shifts, financial incentives, and a gradual reshaping of the entire energy grid. Roman-inspired concrete faces a similar landscape. It is not enough to have a better product, you must change the ecosystem in which it is used. This requires patient advocacy, visionary pilot projects that demonstrate success, and a gradual shift in how we calculate value from short-term cost to long-term legacy. To truly overcome these systemic barriers, we must move beyond the general promise and scrutinize the material's very composition, asking if there are inherent traits that could be redesigned for modern compatibility. That final coarse ingredient in the Roman mix was far from simple rubble. While we focus on the lime and the ash, the Romans gave equal care to the stones they bound together, selecting not just any rock but specific materials that became active partners in the chemistry. This was the alchemy of the aggregate. They favored lightweight, porous volcanic tuff, crushed brick, and other reactive stones. Understanding these were not inert filler, but integral components of a unified system. Modern concrete often fails at the boundary between the paste and the stone, a weak interface where cracks easily propagate. Roman petrographers, scientists who study rocks under microscopes, reveal why this wasn't a problem for the ancients. By examining thin slices of 2,000-year-old concrete, they see something remarkable. The binder didn't just surround the aggregate, it infiltrated it. The reactive, porous surfaces of tuff or brick allowed the lime-rich paste to seep into its microscopic pores and crevices. Over centuries, a slow chemical conversation occurred here, too. Silica and alumina from the aggregate itself dissolved into the alkaline paste, fostering the growth of strengthening minerals right at this critical boundary. The result was a perfect mechanical lock and a seamless chemical transition from aggregate to binder, eliminating that weak plane of failure. This is why a chunk of Roman concrete often breaks right through the aggregate stones, not around them. They are so thoroughly bonded they become one monolithic material. The choice of aggregate was also of practical engineering. Volcanic tuff, for instance, is naturally lightweight and full of air pockets. Using it in massive structures like the dome of the Pantheon dramatically reduced the overall weight and the outward thrust on the supporting walls. Those same air pockets provided superior thermal insulation, a vital property for buildings like the baths of Caracalla, where maintaining vast pools of heated water was essential. There, engineers often used crushed brick, known as the aggregate. This was not merely recycled construction waste. The fired clay of the brick was itself a source of additional alumina and silica, contributing its own potential to the long-term chemical reaction. It was a brilliant, sustainable loop, turning old materials into the enduring heart of new ones. This holistic view reveals the true sophistication of the Roman system. Every component, from the reactive lime clasts to the specific volcanic ash to the carefully chosen aggregate, was selected for its chemical compatibility and its contribution to a single, long-term performance goal. The formula was never a one-size-fits-all solution, it was a deeply local technology. Builders near volcanoes used tuff, those in regions with ample clay used brick, and they always tailored the mix to the structure's purpose, whether it needed to be lightweight, insulating, or supremely strong. This intimate connection to local geology and material flows created a resilience that was literally baked into the landscape, a final lesson in building not just on the land, but with it. A Roman aqueduct in Gaul shares no identical twin with a harbor inn. Each structure is a unique chemical fingerprint, a direct reflection of the ground upon which it stands. This was not a limitation of Roman engineering, but its crowning intelligence. By mastering the art of local adaptation, Roman builders achieved a form of profound, pre-industrial sustainability, weaving their infrastructure directly into the geological fabric of the empire. They understood that the true secret of a durable material lay not in imposing a single, rigid formula everywhere, but in listening to the land and letting its resources dictate the recipe. This geographical wisdom meant that transport of heavy, bulky materials over vast distances was minimized, a logistical and economic. The empire's concrete was not a monolithic product, but a family of related technologies, each branch optimized for its local environment. Archaeologists using geochemical analysis can now trace the origin of a concrete sample with remarkable precision, not to a century, but to a specific quarry or volcanic deposit. The Pozzolana that built the ports came from the slopes of Vesuvius. In the Aegean, builders used the reactive Santorini earth. In regions devoid of volcanic ash, such as parts of Britain or North Africa, they found brilliant alternatives. Crushed ceramic, known as, became a ubiquitous substitute. Discarded pottery and roof tiles, pulverized into a powder, provided the necessary silica and alumina to react with lime. This was more than recycling. It was a sophisticated understanding that fired clay possessed a latent reactivity, a potential waiting to be unlocked by the alkaline bath of lime mortar. The Roman builder's manual was not a single scroll, but a living knowledge of regional material libraries. Lime itself varied in quality and purity depending on the local limestone. Builders learned to adjust their mixes accordingly, calibrating the proportions of lime based on the specific chemical character of what was available at hand. This localization created a powerful synergy. A concrete made with materials from a specific environment was often inherently better suited to withstand that same environment's particular stresses. Whether it was the salt spray of the coast or the freeze-thaw cycles of a highland province, the Gard Aqueduct in southern France stands as a majestic testament to this principle. Its builders did not import exotic volcanic ash from Italy. Instead, they used the golden limestone from quarries right beside the river garden itself. The aggregate was this local stone, and the binder was a lime mortar, likely enhanced with whatever fine materials they could source locally, perhaps even crushed brick. The result is a structure that doesn't just cross the landscape, it emerges from it. The concrete and the bedrock share a common origin, creating a visual and chemical harmony that has endured for two. The aqueduct's resilience is a product of this deep locality, a conversation between human design and regional geology. This approach offers a crucial, counterintuitive lesson for our modern globalized construction industry, which often ships standardized materials across continents. The Roman model suggests that sustainability and durability might be found not in universal sameness, but in intelligent, place-based adaptation. It forces us to ask, what material libraries exist in our own backyards, whose potential we overlook in favor of imported solutions? And this line of thinking inevitably leads to a more speculative frontier, one that wonders if the Romans, in their relentless experimentation, discovered even more hidden activators beyond ash and brick. The enduring strength of Roman concrete has, over centuries, inspired as much legend as legitimate science. A persistent piece of folklore suggests the mix contained mystical additives, from animal blood to goat's milk, ingredients thought to impart supernatural durability. These tales, while colorful, miss the real magic entirely. The true sophistication of the formula lies not in exotic components, but in the profound chemical understanding the Romans achieved through relentless, practical experimentation. Their secret was a mastery of process and proportion, not a hidden vial of magical essence. By separating these persistent myths from the chemical facts, we can finally appreciate the genuine, replicable genius of their technology. One widespread misconception is that Roman concrete sets and hardens underwater through some unique, instant chemical trick. The reality is more gradual and relies entirely on the reaction we've already explored. When the Romans built harbor works, they constructed wooden forms directly in the sea and poured in their hot lime, ash, and aggregate mixture. The seawater did not cause an immediate magical set. Instead, it initiated the long-term chemical conversation. The water helped transmit ions and maintain the moisture needed for the slow, continuous formation of calcium silicate hydrate gels, and eventually, the strengthening crystals like. The setting was actually slower than modern concrete, a patient curing that built strength over years and decades, not days. This demystifies another common oversimplification, the idea that seawater was mixed directly into the batch. It was not. Seawater was the long-term environmental partner, not an initial ingredient. The concrete gained its legendary marine resilience through centuries of ion exchange, not from being mixed with brine on the beach. The belief that all Roman concrete was uniformly indestructible is another myth that crumbles under scrutiny. The quality varied significantly across the empire and across different types of structures. A private villa's foundation mortar was often a simpler, weaker mix compared to the engineered marvel of an imperial aqueduct or a military harbor. Builders adapted their recipes based on local material availability, budget, and the importance of the project. Archaeologists and materials scientists, through core sampling and analysis, can trace this variation. They find that the most durable maritime concrete consistently used the highest quality, reactive pozzolana, and adhered to the meticulous hot mixing process. Lesser structures, built with inferior local materials or rush techniques, have indeed succumbed to time. This variation is crucial because it confirms that the legendary durability was not a happy accident, but the direct result of intentional, high-quality engineering when it mattered most. A related piece of popular speculation often tries to link Roman concrete to even older, supposedly lost technologies, like a mythical Egyptian concrete used to build the pyramids. This comparison, however, conflates very different material sciences. The Egyptians used gypsum and lime-based mortars for binding stone, but they did not develop a true hydraulic concrete that could set underwater and gain strength through chemistry. Their achievements were monumental, but in a different material category. The Roman development was a distinct, advanced innovation, well documented in their own texts and now in their ruins. There is no single, universal, ancient concrete secret. There is the specific, chemically explainable Roman formula. Clearing away these layers of myth and oversimplification does more than satisfy historical curiosity. It has direct, practical implications for the preservation of the ancient structures themselves. When conservators mistakenly believe a material is mystically invulnerable, they might fail to monitor real, slow degradation processes. Understanding that Roman concrete is a dynamic chemical system allows for smarter preservation. Experts can now assess the health of a 2,000-year-old wall by analyzing its mineralogy, checking for the continued presence of reactive lime clasts, and ensuring environmental conditions that support its ongoing self-healing chemistry rather than hinder it. The true legacy of this demystification is empowerment, replacing awe with understanding, and legend with a blueprint we can actually use. This clarity finally brings us to the threshold of the most practical question of all. How do we take this ancient, now understood science and weave it into the very fabric of our modern world? From the streets we walk to the policies, we write a conservator's trowel hovers over a 2,000-year-old crack in the Colosseum. This moment captures a profound modern dilemma, one that pits our reverence for the past against the limits of our present knowledge. When a Roman monument needs repair, what material do we use? The obvious choice, modern Portland cement mortar, is strong, readily available, and familiar to every mason. Yet, for the ancient concrete it is meant to save, this modern material can be a death sentence. This is the conservation conundrum, where the wrong kind of help does more harm than neglect. The core of the problem is a fundamental chemical incompatibility. Modern cement is dense, rigid, and far less permeable than Roman mortar. When it is used to patch an ancient wall, it creates a hard, impermeable shell over a softer, more porous substrate. Rainwater and humidity, always seeking a path, become trapped behind this modern seal. With nowhere to go, the moisture accumulates. In winter, it freezes and expands. Salts from the atmosphere dissolve and recrystallize. This relentless internal pressure has nowhere to vent except outward, through the original Roman material. The result is a heartbreaking phenomenon known as spalling, where the ancient concrete itself begins to blister and flake away, destroyed by the very patch meant to save it. Past generations of restorers, working with the best intentions and the best materials of their time, inadvertently accelerated the decay of the monuments they loved. Today, world-renowned conservators at sites like the Colosseum and the Roman Forum operate under a guiding principle: minimal intervention. Their goal is not to make the structure look new, but to ensure its stability for future generations with the possible touch. This often means carefully cleaning surfaces, installing nearly invisible supports to arrest structural movement, and using soft, sacrificial mortars for temporary fills, all while documenting every step. The dream, however, is to move beyond mere stabilization to true, chemically compatible repair. This drives a dedicated branch of research, where archaeologists and materials scientists collaborate to create authentic replica mortars. The challenge is immense. They must match not only the appearance and texture of the original, but its physical and chemical behavior, its porosity, its flexibility, and its long-term reaction to the environment. An illuminating case study is the ongoing restoration of Trajan's Market, a vast commercial complex in the heart of Rome. Here, conservators face a mosaic of decay, with sections eroded by time and others damaged by well-meaning but damaging 20th century repairs. The project involves a meticulous autopsy, carefully removing those hard cement patches to relieve the trapped moisture. For new fills, researchers have developed custom blends using hydrated lime and finely ground brick dust, a close cousin to the Roman, aiming to replicate the original material's soft permeability. The work is painstakingly slow, each repair a small experiment in relearning an ancient craft. It raises a reflective question for our era: how do we act as stewards for a technology we are only beginning to fully comprehend? We must repair these structures without arrogantly overriding their material biography. This practical, hands-on struggle in the shadow of the emperors brings us full circle, back to the fundamental chemistry we started with. The quest for a compatible repair mortar is, in essence, the quest to recreate the self-healing system. It forces us to ask not just what the Romans used, but how we can make it work today, not for grand new harbors, but to honor the old ones. This intimate act of preservation may be the most sincere form of rediscovery, a humble dialogue with the past that ensures its voice continues to speak. At the very heart of both ancient and modern concrete lies a hidden, universal glue. This is the calcium silicate hydrate gel, a substance so fundamental that materials scientists often refer to it simply as CSH. It is the nanoscale binder that holds everything together. The microscopic mortar that gives concrete its strength. Yet, not all CSH gels are created equal. The profound difference between a crumbling modern pier and an eternal Roman harbor can be traced directly to the atomic architecture of this very substance. While both materials form this gel, the Roman recipe engineers a version that is inherently more stable, more durable, and designed to last for. To understand why, we need to look at its chemical recipe card, the ratio of calcium to silica. Modern Portland cement produces a CSH gel with a very high calcium to silica ratio. Picture this gel as a hastily assembled structure built with too many of one type of block. The calcium-rich blocks are eager to react, but they leave the overall arrangement somewhat loose and disordered, with tiny pores and a tendency to break down over time. Especially when attacked by aggressive chemicals like seawater chlorides. The Roman process, with its perfect marriage of lime and reactive pozzolana, crafts a different gel entirely. It has a much lower calcium to silica ratio. Using our building block analogy, this is a structure built with a more balanced, diverse set of materials. The silica-rich blocks from the volcanic ash interlock, with the calcium in a more densely packed arrangement. This creates a gel that is less porous, more crystalline in its interfaces, and far more resistant to chemical attack. Chemists who study these materials use a helpful comparison. The modern CSH gel is like a hastily stacked pile of firewood, with gaps and irregularities. The Roman version is more like a carefully laid stone wall, where each piece is fitted and locked into place, creating a monolithic whole. Spectroscopic data from samples reveals this stark contrast. The atomic signature of the Roman gel shows sharper, more defined peaks, indicating a more ordered and stable atomic neighborhood. The modern gel signature is broader and more diffuse, a sign of its inherent disorder and vulnerability. But the Roman genius goes beyond creating a superior gel at the moment of pouring. Their system is dynamic. Those embedded lime clasts and the reservoir of reactive pozzolana ensure the chemistry never truly stops. Over centuries, as moisture travels through the concrete, it slowly dissolves a little more silica from the ash and a little more calcium from a lime clast. These ions then meet and precipitate out as new CSH gel, continuously repairing and, crucially, densifying the existing network. It is a process of perpetual renovation at the atomic scale. The gel becomes less like a static glue and more like a living tissue, constantly reinforcing itself from within. This slow, ongoing reaction explains why cores from ancient harbors show the concrete gets denser and harder with age. The gel network is not degrading, it is maturing, becoming more stone-like with every passing decade. This understanding of the universal binder reframes the entire Roman achievement. They were not just builders, they were master, though they would never have used the term. They engineered a material system that optimizes the most fundamental component of concrete itself. Their formula is a timeless model for resilience, proving that true strength is not found in rigid resistance, but in a balanced, adaptable chemistry that grows more unified with time. That same chemical partnership with the sea now offers a blueprint for our own turbulent future. Roman concrete stands not as a relic, but as a profound prototype for designing resilience in an age of rising seas and intensifying storms. Its core lesson is radical. Instead of fighting the environment with brittle barriers, we can design infrastructure that listens, adapts, and even draws strength from the very forces that threaten it. This is not a metaphor. It is a direct material science parallel for our era of climate adaptation. Planners working on coastal resilience are now urgently seeking materials that do not just resist water, but manage it intelligently over centuries. The Roman formula provides a tangible model. Its self-healing nature addresses the increased cracking from more frequent and powerful storm surges. While its ability to sequester minerals from seawater mirrors the kind of active, beneficial exchange we need to design into our own defenses. Think of a modern coastal city's dilemma. Its concrete are constantly patched, a costly and losing battle against chloride corrosion and wave impact. A breakwater built with Roman-inspired principles would operate differently. Each storm-driven crack would trigger an autonomous repair, and the constant exposure would slowly foster internal mineral growth, making the barrier denser and stronger over decades, not weaker. This transforms a liability, constant maintenance, into a legacy of accumulating strength. The material's inherent properties align with multiple climate challenges. Its significant thermal mass, a result of its dense, stone-like composition, could be harnessed in buildings to naturally buffer against temperature extremes, reducing energy demands for heating and cooling. More fundamentally, its dramatically lower embodied carbon, when made with modern, directly addresses the urgent need to slash construction emissions. Here, ancient durability meets modern sustainability, creating structures that are both long-lasting and low-carbon from their very inception. This convergence points toward a necessary evolution in our building codes. Current standards prioritize immediate strength and speed, but climate resilience demands we add new metrics: long-term durability, passive adaptation, and carbon accounting. Future codes could incentivize materials that demonstrate self-healing capabilities or that use industrial byproducts, rewarding the kind of holistic thinking the Romans embodied. Envision a not-so-distant project, a new district in a flood-prone city. Its foundational slabs use a carbon-sequestering, Roman-inspired concrete, locking away greenhouse gases. Its riverfront promenade is edged with porous, mineral-growing blocks that clean stormwater runoff. And just offshore, a reef-like breakwater of the same material dampens wave energy while providing habitat for marine life. This is not science fiction. It is the logical application of a 2,000-year-old material science principle, redesigned for the 21st century. The cultural impact of choosing such durability would be profound. It would shift our relationship with the built world from one of planned obsolescence to one of intergenerational stewardship. We would begin to construct legacies, not just buildings, creating infrastructure that tells future generations we considered their world in our designs. What story do we want our concrete to tell in 1,000 years? One of short-term expediency, or one of thoughtful, resilient partnership with the planet? The Pantheon's dome is more than an architectural marvel. It is a physical declaration. In its perfect, unsupported hemisphere, we see the ultimate expression of a civilization that believed in permanence, in imposing its order upon the world for all time. This was the Roman worldview, ambitious, practical, and monumentally confident, and their concrete was the indispensable tool that turned that vision into enduring stone. To understand Rome is to understand how this material became the literal bedrock of their identity, enabling an empire to think and build on a previously unimaginable scale. Architectural historians note that before concrete, Roman architecture was constrained by the logic of cut stone and brick. Grand spaces required forests of columns to hold up heavy lintels and roofs. But with the advent of concrete, everything changed. The material was not merely a new substance, it was a new language of form. It could be poured into wooden molds, taking any shape the architect could dream. It allowed for the creation of vast, uninterrupted interior spaces, free from obstructive supports. This versatility was the key that unlocked the iconic Roman architectural vocabulary: the soaring arch, the complex groin vault, and the monumental dome. These were not just aesthetic choices, they were political and cultural statements. A vaulted basilica conveyed the grandeur of imperial law. A massive dome, like that of the Pantheon, symbolized the heavens themselves, brought to earth under Roman mastery. The very act of building these structures, and building them rapidly across 3 continents, was a core component of that ideal of. It was a demonstration of logistical power, engineering genius, and a commitment to creating a unified, civilized world. Concrete was the engine of this imperial project. It allowed for the standardization and speed necessary to imprint Roman culture, onto diverse landscapes. From the windswept border of Hadrian's Wall in Britain to the deserts of North Africa, the same material principles built the forts, baths, and administrative centers that defined Roman rule. The infrastructure was both practical and symbolic. The aqueducts that brought fresh water to cities were not just feats of engineering, they were monuments to civic care and control over nature. The harbors, like the one at, secured the grain supply that fed Rome's million inhabitants, stabilizing the empire's very heart. An illuminating example is the Basilica in the Roman Forum. Constructed in the early 4th century, its colossal vaulted nave was made possible entirely by concrete. The speed of its construction, using poured material instead of countless individual stone blocks, showcased the state's ability to marshal resources and create awe-inspiring public space on demand. This rapid, monumental building capability was a tool of governance, impressing citizens and visitors alike with the immutable power of Rome. Classicists often describe concrete as the physical manifestation of the Roman desire for legacy. While Greek civilization left us ideals carved in marble, Rome left us a functional world cast in concrete. Their ambition was to build a civilization that would never end, and in a profound way, the material they mastered has granted that wish. The ruins that still stand are not just leftovers, they are active participants in our present, continuing to shape our understanding of urban space, engineering, and empire. This cultural perspective reveals a fundamental truth. The materials a civilization masters do not just serve its needs, they shape its ambitions and ultimately define its memory. The Romans chose a material that partnered with time, and in doing so, they built a dialogue with the future. The Romans were not alone in their quest for a material that could heal itself. Today, in laboratories from the Netherlands to Japan, a new generation of smart materials is emerging, designed with the same core ambition to repair damage from within. This modern field, often called self-healing materials, creates a fascinating parallel to the ancient Roman technology, proving that the most advanced ideas sometimes find their inspiration in the distant past. Among the most prominent of these is bioconcrete, a material that introduces a tiny, living workforce to the mix. Scientists embed dormant bacterial spores, along with a food source like calcium lactate, into the concrete matrix. When a crack forms and water seeps in, it awakens the bacteria. The microbes consume their nutrient store, and as part of their metabolic process, precipitate calcite, a form of calcium carbonate, effectively gluing the crack shut from the inside out. The conceptual similarity to Roman concrete is striking. Both systems rely on a built-in repair mechanism that remains dormant until activated by an environmental trigger, water. For the Romans, the trigger reactivates a chemical reservoir, the lime clast. For bioconcrete, it awakens a biological one, the bacterial spore. Materials scientists who study both systems note this shared design philosophy, a shift from viewing materials as static to viewing them as dynamic systems. They achieve repair through entirely different pathways, one purely chemical and mineralogical, the other microbiological, but they answer the same fundamental challenge. When experts compare their practical potential, interesting contrasts in efficiency, cost, and scalability emerge. The Roman system is elegantly simple, using only natural mineral ingredients. Its repair process is slow, steady, and can theoretically continue for centuries, as long as reactive lime and silica remain. Bioconcrete offers a potentially faster repair cycle, with cracks sealing in weeks, but it faces questions about the long-term viability of the bacterial spores and their nutrient supply over decades. The cost of producing the specialized bacterial capsules is also currently higher than traditional concrete additives, though proponents argue the lifetime maintenance savings justify the investment. Beyond bioconcrete, the inspiration from nature and history is fueling a wider revolution in smart materials. Chemists have developed self-healing polymers that mimic the clotting process in human skin, using microcapsules filled with a healing agent that rupture upon damage. Other composites contain vascular networks, like tiny blood vessels, that can deliver a liquid healing agent repeatedly to a damaged site. There is even concrete that uses embedded glass capillaries filled with an epoxy resin that flows into cracks. Each of these approaches seeks to endow inert materials with a lifelike resilience. To visualize this parallel journey, picture two laboratory samples side by side. On one side, a block of Roman-inspired concrete made with hot mixed lime and pozzolana bears a hairline crack. It is placed in a tank of circulating seawater. Over 2 weeks, a white, crystalline blush slowly fills the fissure, a silent chemical precipitation sealing the wound. On the other side, a standard concrete block with embedded bacteria and nutrients sports a similar crack. Water is introduced. In a comparable, a white, crusty layer of bacterial calcite emerges, bridging the gap. The visual result is remarkably similar, but the unseen mechanisms are worlds apart, one a geological process, the other a biological one. This comparison is more than a neat laboratory demonstration. It is a validation of a timeless principle. It shows that the Roman approach, achieving self-repair through carefully designed chemistry, was a form of advanced material science ahead of its time. Their work is no longer just a historical curiosity. It is a foundational case study in a modern scientific field. The ancient ruins are now seen as a proof of concept, demonstrating that passive, embedded repair systems are not just possible, but can be astonishingly durable. This validation through rigorous modern testing gives engineers the confidence to look backward for inspiration as they build forward. It raises a compelling question for our innovative age. If a 2,000-year-old idea can hold its own against cutting-edge biotechnology, what other forgotten principles might be waiting in the past? Ready to solve the problems of our future, a pristine cylinder of Roman-inspired concrete sits in a testing chamber, its surface etched with a single hairline crack. Around it, engineers monitor screens displaying graphs of pressure, temperature, and electrical resistance. This is not a scene from science fiction, but the critical, unglamorous work of standardization, where ancient chemistry meets the rigorous language of modern engineering codes. Before this material can ever support a bridge or shield a coastline, it must prove its worth not through centuries of observation, but through a battery of accelerated, quantifiable tests designed to compress into months. The pathway from a promising laboratory mix to a certified building product is a marathon of validation, governed by global standards organizations like a STM International. Their committees, composed of engineers, scientists, and industry experts, face a unique challenge: how to write a rulebook for a material whose greatest strength is a performance history written in ruins. The process begins with translating historical anecdotes into cold, hard data. Engineers cannot specify a material because it worked for 2,000 years. They need numbers, predictable curves, and safety factors. This requires a suite of tests that measure key performance indicators under extreme, accelerated conditions. One of the most critical is the rapid chloride migration test. A sample of the concrete is placed in a setup where one end is exposed to a concentrated salt solution, and an electrical field is applied, driving chloride ions into the material at an accelerated rate. After a set period, the sample is split open and sprayed with a chemical indicator that turns silver nitrate purple where chlorides have penetrated. For conventional concrete, the purple stain often goes deep, revealing a highway for corrosive ions to reach steel reinforcement. For a successful Roman-inspired mix, the stain should be shallow or existent, visually proving its innate resistance to the very element that destroys modern marine structures. This test provides a quantifiable metric, a chloride diffusion coefficient, that engineers can plug directly into their durability models for a bridge deck in a coastal environment. But resistance is only part of the story. The material must also demonstrate its active healing capability. Researchers have developed clever methods to quantify this. A common procedure involves pre-cracking a sample to a precise width, often using a controlled bending apparatus. The cracked sample is then placed in a fog room or immersed in a solution mimicking seawater. At regular intervals, its flexural strength is retested, or the crack width is measured under a microscope. The goal is to chart a recovery curve, showing how much strength the material regains or how much the crack closes over days or weeks. This data transforms the poetic idea of self-healing into an engineering parameter, a healing efficiency percentage that can be compared across different mixed designs. Alongside this, the material must endure brutal environmental simulations. In a freeze-thaw cabinet, samples are subjected to hundreds of cycles, rapidly soaking in water and then freezing solid, a process that causes conventional concrete to crack and spall from internal pressure. A Roman-inspired mix must show minimal scaling and mass loss, proving its poor structure and binder can withstand the expansion of ice without catastrophic failure. Perhaps the most daunting challenge is simulating seismic forces. On a massive shake table, a scaled-down structural element, like a column or beam made with the novel concrete, is subjected to recorded ground motions from historic earthquakes. Engineers instrument it with dozens of sensors measuring acceleration, displacement, and strain. The test seeks to answer a pivotal question: does the material's flexibility and self-healing potential translate into better performance during and after a seismic event? Can it absorb energy through, and then begin to autonomously repair those in the aftermath, preserving structural integrity for aftershocks? The data from these tests feeds into complex computer models that predict how an entire building or bridge made with such material would behave, allowing for the development of new seismic design guidelines. Beyond these specialized trials, the material must also pass all the standard tests required of any concrete compressive strength over time, tensile strength, creep, and shrinkage. The long-term volume stability is particularly scrutinized, as engineers need assurance that a massive pour will not develop destructive internal stresses over decades. Members of standards development committees describe this as a iterative dialogue. A proposed new specification starts as a draft, informed by academic research and pilot project data. It is then subjected to rounds of balloting and commentary from the entire committee, a process that ensures every potential weakness is examined and every safety concern is addressed. The goal is to create a living document, like an ASTM standard, that provides a reliable recipe and a set of pass-fail criteria for manufacturers and a clear set of design rules for structural engineers. This rigorous validation is the indispensable bridge between a fascinating historical rediscovery and a material that can be responsibly for a school, a hospital, or a power plant. It shifts the conversation from what the Romans achieved to what we can reliably predict, transforming timeless observation into trustworthy calculation. This meticulous process of testing and certification does more than just a new building product. It becomes a form of education in itself, teaching us a new vocabulary for durability that our current standards simply lack. The most profound shift may not be happening on a construction site, but inside a university lecture hall. For over a century, engineering textbooks have presented a linear narrative of progress, where modern Portland cement represented the pinnacle of material science, an inevitable improvement over the crude mortars of the past. The rediscovery of Roman concrete has shattered that assumption, forcing a fundamental rewrite of how we teach the next generation of builders. Professors of civil engineering now describe a pivotal moment in their curriculum, where they must present students with a paradox. How could a 2,000-year-old formula outperform the product of our most advanced laboratories? This question is no longer a rhetorical flourish. It is the central theme of a new module appearing in materials science courses from to Cambridge. The goal is to move beyond teaching concrete as a set of standard mixes and strength tables. Instead, educators are integrating the Roman harbor as a primary case study in long-term performance. Students are presented with core sample data, microscopic imagery of lime clasts and crystals, and the chemical models of self-healing. They are asked not just to calculate a material's strength at 28 days, but to model its likely condition after 100 years of seawater exposure. This reframes the entire discipline. A professor at the Massachusetts Institute of Technology explains the pedagogical shift. We are teaching students to design for time, not just for load. We are asking them to consider the environmental dialogue of a material, to think about what happens after the ribbon cutting, long after their own careers have ended. This new philosophy embraces learning from failure in a dual sense. Students analyze the predictable, premature failures of modern marine concrete due to steel corrosion, a direct consequence of a material choice made a century ago. Alongside it, they study the success of the Roman breakwater, a structure whose material choices have yielded a 2,000-year victory. The contrast is stark and instructional. It teaches humility and a broader systems thinking, where the consequences of an engineering decision ripple across centuries. To make this tangible, new laboratory exercises are being developed. Instead of only testing the compressive strength of newly cast cylinders, students might be given a sample of modern concrete and a fragment of ancient Roman mortar. They subject both to accelerated weathering cycles, or they create micro cracks and observe them under microscopes while exposed to moisture. Witnessing a modern sample deteriorate while the ancient one shows signs of mineral deposition and crack filling is a powerful, hands-on lesson no textbook paragraph can match. This experimental approach cultivates a more holistic design philosophy. It encourages future engineers to ask questions their predecessors might not have considered. What is the embodied energy of this material over 500 years? Does it have a capacity for autonomous repair? Can it work with its environment rather than merely resisting it? These are the questions that will define resilient design in the coming century. Reflecting this shift, a leading publisher is preparing a new edition of a classic civil engineering textbook. In it, a chapter on the history of construction materials no longer relegates Roman concrete to a brief introductory passage. It is presented as a full, contemporary case study in sustainable material design, complete with chemical equations, cost analyses, and modern replication methods. It sits not in the past, but alongside chapters on high-performance composites and smart materials, presented as an equally valid and profoundly instructive technology. This educational evolution is crucial, for it seeds the future. The students in these classrooms today will be the ones specifying materials for the that protect our cities in 2050, and the deep geological repositories that must stand guard for. By teaching them to value durability as much as efficiency, to see time as a design parameter, we are not just updating a curriculum, we are quietly laying the foundation for a more enduring world. The lesson from Rome is now a required course, and its final exam will be the legacy we leave in stone. Science rarely announces its breakthroughs with a fanfare. More often, they whisper from the corner of a laboratory, in the form of an anomaly that everyone else has learned to ignore. The full chemical secret of Roman concrete remained locked away for so long not because the clues were missing, but because we had trained ourselves to misinterpret them. For generations, those distinctive white lime clasts speckled throughout ancient samples were textbook examples of a mistake. They were the clear evidence, so the thinking went, of uneven mixing or low-quality materials, the ancient equivalent of lumps in a poorly made batter. This assumption was a perfect example of a paradigm, a mental model so strong it blinded researchers to alternative explanations. The real story of rediscovery is one of serendipity meeting prepared curiosity, where scientists asking different questions finally looked at the same old stones and saw something entirely new. A pivotal moment came not from a grand expedition to a Roman ruin, but from the ray examination of a core sample that had been sitting in a university archive for decades. Collected in the 1990s from a Roman marine structure, it had been studied for its general composition and then filed away. Years later, armed with more powerful electron microscopes and a growing interest in ancient materials, a new generation of researchers pulled it from the shelf. They were not specifically looking for a self-healing mechanism, they were conducting a broad mineralogical survey. But as they zoomed in on the interface between a lime clast and the surrounding mortar, they saw something that the old assumption. The edges of the clast were not sharp and separate, as an inert lump would be. Instead, they showed signs of dissolution and a fuzzy, active boundary where chemistry was clearly at work, even after two. This was the first quiet clue that these features were not mistakes, but participants. The chance discovery echoed a classic pattern in the history of science. For centuries, doctors dismissed stomach ulcers as a product of stress and diet, until two researchers, Barry Marshall and Robin Warren, dared to ask if a bacterium could survive in the acidic environment of the stomach. Their colleagues were skeptical, even dismissive, because the paradigm said it was impossible. Yet by questioning the assumption and connecting disparate observations, they revolutionized medicine. Similarly, the lime clasts in Roman concrete were an ulcer in the paradigm of ancient technology, a persistent anomaly waiting for someone to ask a different question. That question often comes from the edges of a field, or from a mind unburdened by too much conventional wisdom. In one research group, it was a graduate student pondering the material who voiced a simple, pivotal thought. What if the heat from the lime slaking wasn't just a dangerous byproduct, but the whole point? What if the Romans weren't just putting up with the violent reaction, but were harnessing it? This "what if" shifted the entire investigation from analyzing a static substance to reverse engineering a dynamic process. It led to the key experiment of deliberately creating hot mixed mortar with large lime inclusions, then mechanically cracking it and observing its behavior in water. The team watched, almost in disbelief, as the white, crystalline blush of new material filled the fissure. The anomaly had been transformed into a function, the mistake into a masterpiece of engineering. This narrative of serendipity underscores a profound truth about discovery. It is not a straight line from question to answer. It is a meandering path paved with overlooked details, where breakthroughs often arrive while you're looking for something else entirely. The researchers reflecting on this journey often emphasize the role of basic, curiosity-driven science, work done without a specific commercial application in mind, simply to understand how the world works. It was this foundational curiosity that allowed them to pause at the anomaly, to spend time on the why is this here, instead of dismissing it and moving on. Their tools provided the magnification, but it was their mindset that provided the vision. They had to overcome the bias of presentism, the unconscious belief that our modern methods must be superior, and consider that an ancient builder might have intentionally chosen a path we had written off as primitive. This story, still unfolding in labs today, naturally extends an invitation. If professional scientists, revisiting archived samples with new perspectives, can crack a 2,000-year-old code, what other historical puzzles might be solved by a fresh pair of eyes? This brings us to the untapped potential of looking beyond the laboratory, to the collective curiosity of the wider world. The final chapter of this discovery is not written by scientists alone, but by anyone with a curious eye. This global detective story now welcomes a new kind of investigator, the public observer, turning every ancient wall and weathered pier into a potential piece of evidence. You do not need a doctorate to contribute to this unfolding narrative of resilience, only a willingness to look closely at the history in your own backyard. The growing field of public archaeology thrives on this very principle, recognizing that local knowledge and community observation are invaluable resources for mapping our shared past. Consider the story of a small town in southern France, where residents walking along an old medieval wall noticed something peculiar. Sections repaired with a certain gritty, pinkish mortar showed almost no wear, while other patches crumbled away. Their observations, shared with a regional archaeological society, helped identify a forgotten local source of earth that medieval masons had used, a direct echo of Roman practice. This kind of citizen-led discovery is not an isolated event. Across Europe and the Mediterranean, community groups are partnering with universities to document and sample mortar from lesser-known Roman sites, creating a crowdsourced database of ancient material recipes. These amateur historians provide crucial context, often knowing the oral histories and land use patterns that official records miss. Their careful photographs and notes become the raw data that helps experts spot patterns and anomalies across vast distances. How can you engage in this collaborative endeavor? The pathways are more accessible than ever. Numerous organizations offer structured ways to participate. Platforms like host digital archaeology projects, where you can help classify images of artifacts or map features from aerial surveys from your own computer. Institutions like the Archaeological Institute of America run public lectures and often seek volunteers for local site stewardship programs. For those with a deeper interest, many university-led digs offer field school opportunities for non-specialists, providing hands-on training in excavation and documentation. Even simpler acts have impact. Reporting unusual durability in a local historical structure to a preservation society can flag a material worth scientific study. Supporting archaeological research through reputable crowdfunding platforms directly fuels the analysis of samples, including the petrographic thin-sectioning that reveals a concrete's inner crystalline world. The key is to connect your curiosity to the network. Start by exploring the open-access journals where many of these Roman concrete studies are published, often available through university libraries or sites like Google Scholar. Visit local museum collections and look closely at their architectural fragments, asking questions about the materials you see. This inclusive perspective transforms the story from a distant scientific revelation into a living, participatory science. It reminds us that the stones themselves are only part of the record. The human curiosity that questions them completes it. As we begin to synthesize everything we've learned, this collaborative spirit reframes the ultimate meaning of the rediscovery. It is not just about rebuilding with an ancient recipe, but about rebuilding our relationship with the past as an active, shared inquiry, where every observer can help write the next page in the manual for the ages. 4 pillars now stand clear from the dust of history, a framework for building not just concrete, but a different kind of future. The Roman concrete revolution was not a single trick, but a symphony of interconnected principles, a system where each part supported the others to create something greater than the sum of its ingredients. The first pillar is the foundation itself, the use of reactive. This is the principle of activation. The Romans didn't just use aggregate, they used a material like volcanic ash or crushed brick that was chemically hungry. When combined with lime, this reactive powder didn't just sit there. It dissolved and recombined, forming the dense, durable gel that is the true heart of the binder. It transformed inert dust into a chemical partner. The second pillar is the engine of resilience, the hot mixing technique with quicklime clasts. This is the principle of embedded potential. By mixing in chunks of slaked quicklime, the Romans baked a repair kit directly into the material. The violent heat of the reaction created a unique chemistry, and those white inclusions sat dormant for centuries, waiting for water to trigger their transformation into crack-sealing crystals. It was a design for time, engineering not just for the moment of pouring, but for every moment of stress to come. The third pillar is the long-term growth strategy, the cultivation of beneficial crystalline phases. This is the principle of maturation. The Roman mix created the perfect chemical nursery for minerals like amphilepsite to slowly grow. These interlocking plates and needles didn't exist at the start. They were born from the patient reaction between the concrete and its environment, weaving a microscopic armor that made the material harder and denser with every passing decade. Strength was not a fixed property, but a process. The fourth and final pillar is the overarching philosophy, the design for environmental interaction. This is the principle of partnership. The Romans did not see seawater or weather as forces to be defeated with brute resistance. They designed a material that could listen to its surroundings and draw strength from them. Seawater wasn't a corrosive enemy, it was a source of ions that fed the crystalline growth. This shift from resistance to collaboration is perhaps the most profound lesson of all. These 4 pillars do not stand alone. They are a closed loop, an ecosystem in stone. The reactive provides the silica needed for the long-term crystals. The hot mixing ensures the lime clasts are present to activate self-healing. The self-healing maintains the integrity of the material so the slow crystallization can proceed. And the entire system is optimized to thrive in a specific environmental context, whether marine or terrestrial. Thought leaders in sustainable design now point to this framework as a blueprint for modern innovation. It teaches us to move beyond designing static objects and instead design dynamic systems. We must ask, does our material have a source of activation? Does it contain embedded potential for repair? Is it designed to mature and improve over it? And most importantly, is it in a partnership with its environment or a war against it? Imagine a tree in a forest. It is not a static object. It draws nutrients from the soil and air. It heals its own wounds with sap and new growth. It strengthens its structure year after year. and it exists in a symbiotic relationship with the ecosystem around it. Roman concrete operated on similar principles of resilience. It was less like a cast iron shield, designed to take hits until it breaks, and more like a living wood, capable of adaptation and regeneration. This consolidated framework provides a clear mental model, a checklist for durability that transcends ancient history. It gives us a lens to evaluate not only new concretes, but any material meant to last. The question it poses is simple yet revolutionary. Are we building inert products, or are we cultivating resilient systems? This is not just a story about a better concrete. It is the emergence of a new design philosophy, one that could reshape everything we build. The true legacy of the Roman concrete rediscovery may be a paradigm shift, a move from creating static, consumable materials to engineering dynamic living systems. We are learning to design for time, not against it. This is the principle of time-positive design, where a product is not finished when it leaves the factory, but is instead engineered to improve, adapt, and strengthen throughout its entire. The ancient harbor wall is the ultimate proof of concept, a material that entered the world with a built-in capacity for growth. It challenges the foundational assumption of modern manufacturing that decay is inevitable and our only job is to slow it down. What if, instead, we design things to mature? Think of a polymer coating on a bridge that doesn't just resist UV rays, but uses sunlight to catalyze a reaction that continually renews its surface, like a synthetic version of photosynthesis. Imagine a road asphalt embedded with microcapsules of a healing agent that liquefy under the pressure of a forming crack, flowing into the void and hardening, erasing potholes before they ever disrupt traffic. Envision the steel in a skyscraper's frame not as a passive beam, but as an alloy designed to develop a tougher, more corrosion-resistant patina with each passing year, drawing strength from the urban atmosphere itself. This is not science fiction. It is the logical extension of a 2,000-year-old idea. Materials scientists are already exploring this frontier under names like stimuli-responsive materials and four-dimensional printing. These are substances programmed to change their shape, density, or function in response to specific environmental triggers, like temperature, moisture, or stress. A polymer that stiffens under impact to protect, then softens afterward to dissipate energy. A fabric that changes its porosity based on humidity to regulate temperature. These are early steps toward a world where our materials are in constant, intelligent dialogue with their surroundings. The implications stretch far beyond construction. Consider consumer electronics, devices notorious for their planned obsolescence and brittle fragility. A time-positive design approach would ask, could we create a smartphone casing that self-heals minor scratches? Could a battery's chemistry be designed to slowly reconfigure, maintaining a higher capacity for more charge cycles over a decade instead of degrading in 2 years? The goal shifts from selling a replacement to cultivating a long-term relationship with a product that evolves. Futurists who model sustainable economies point to this as a cornerstone. In a circular, waste-free world, products must be built to last and then to be fully reclaimed. Time-positive design makes that longevity active and beneficial, not just passive endurance. An illustrative vision for infrastructure is a building with a built-in health monitor, but not one that merely signals decay. This monitor would track the beneficial chemical maturation of its own concrete, displaying not a remaining, but an increasing strength index. It would report on the growth of strengthening minerals, the consumption of repair agents, and the overall wellness of the structure. The manager of such a building wouldn't plan for demolition in 50 years, but would steward an asset growing more valuable with each century. This expansive perspective reframes our entire relationship with the physical world. It asks us to see not objects, but processes, not endpoints, but beginnings. The Roman concrete did not achieve perfection the day it was poured. It began a chemical journey we are still witnessing. What other materials, currently sitting inert on our shelves or in our landfills, could be redesigned to embark on a similar, purposeful journey? This question pulls the lens back from the microscope to the horizon, from a single chemical secret to a new way of seeing everything we make. The Pantheon's dome began this journey, a silent question cast in stone. We end it not at a finish line, but at a starting point, armed with a blueprint for time itself. The chemical secret of Roman concrete is laid bare, a sophisticated dance of hot mixed quicklime, reactive ash, and an intentional partnership with the elements. It was never a single ingredient or a lost incantation, but a system, a philosophy of resilience written into the very atoms of their world. Modern science has now decoded that language, translating ancient empirical genius into formulas we can test, measure, and most importantly, build upon. This is more than a historical footnote, it is a paradigm shift delivered from the past. The implications ripple outward, touching how we conceive of durability, sustainability, and our relationship with the planet. It asks us to value patience over haste, adaptation over resistance, and legacy over expediency. This story is a powerful testament to human ingenuity across the ages. It humbles our modern assumptions, reminding us that brilliance is not always measured by complexity, but sometimes by profound, enduring simplicity. The Romans built for the eternity they believed in, and in doing so, they left a light for a future they could never see. As we face our own era of environmental and infrastructural challenges, that light is now shining brightly on a new path forward. It inspires us to think in centuries, to design materials that mature like fine wine, and to construct a world that our descendants will thank us for, not one they must rebuild from our rubble. If this exploration of a 2,000-year-old mystery has sparked your curiosity, there are countless more waiting in the shadows of history. We would love to hear which enduring ancient technology fascinates you the most. Share your thoughts below and subscribe to join us as we continue uncovering the hidden stories that shape our understanding of the past and our vision for the future.